So today, we talk about the covariance and the correlation coefficient in addition to functions of two random variables. So the covariance CV of two random variables x and y is the expected value of x minus e of x, y minus e of y, which ends up being the expected value of xy minus the expected value of x times the expected value of y. In a random process, we will talk about this also in more detail, that is xt, kx of t1 and t2 is the covariance of xt1, xt2, which is the expected value of xt1, xt2 minus the expected value of xt1 times the expected value of xt2. This is the autocovariance. This is the covariance. And when you remove this part alone is the autocorrelation. Also, finally, rho x and y is the covariance of x and y divided by square root variance of x, variance of y, which is sigma xy over sigma x, sigma y. That is the correlation coefficient. All right. Last time, we did talk about the joint PDF, the joint PMF of two random variables. Today, we discuss another metric that describes the relation between these two random variables and how they interact together. This is called the covariance of two random variables x and y, which is this expectation that ends up being exy minus ex times ey. In order to think about how it represents the relation between two random variables, let's think about the case where the two random variables are independent. This covariance will end up being 0, right? Because exy will end up being ex times ey, and this becomes a 0. So if your two random variables are independent, in fact, if your two random variables are uncorrelated, this covariance will end up being a 0. As we know, independence implies the random variables being uncorrelated, but not the other way around. Okay, how about that? What is a random process? In fact, Chaghtay Hoja is going to be talking to you about this a lot in the third part of the course, but let's think about a random process. What is a random process? So a random process is, if we think about a random process like this, which is just a random sequence, and that random sequence has multiple versions. So this is version 1, and this is version 2, and this is version 3, and so on and so forth. You can think about this random sequence, which is itself a random process, as a collection of time-varying random variables, a set of time-varying random variables. That being said, here you can think about this as random variable x1, and these are the values it can take, and here random variable x2, and here random variable x3, and so on and so forth. So 1 is for time instance 1, 2 is for time instance 2, 3 is for time instance 3, and so on and so forth. So when you look at a random process and you are willing to identify the inherent randomness inside it, you do these things, the autocovariance and the autocorrelation. So the autocovariance kx of t1 and t2 is the covariance between the two random variables of the random process at times t1 and t2. All right? And it is the expected value of xt1, xt2 minus ext1, ext2. When you are not looking at this term and you're only looking at the first term, it becomes the autocorrelation function, the Fourier transform of which is the power spectral density of the sequence. All right? The last thing is the correlation coefficient, which is a measure that is essentially derived from the covariance of two random variables. It is sigma xy divided by sigma x times sigma y. Can someone tell me what is the range of rho xy. What is the maximum absolute value of rho xy? What is the maximum absolute value of the correlation coefficient between two random variables? Yeah, exactly. This means they are perfectly correlated, okay? Or perfectly uncorrelated because we talked about the absolute value, right? So let's say not perfectly uncorrelated. They are perfectly correlated, but in the reverse direction, okay? So when the absolute value is 1, they are either y equals positive value times x or y equals negative value times x, right? So the range of rho xy is between 1 and 1, and this is our example 1 that we want to prove this thing. All right, so the variance of x is the expected value of x squared minus the expected value of x overall squared. And the variance is a non-negative quantity, and thus e of x squared greater than or equal to e of x overall squared greater than or equal to 0. This is the starting point of our proof, and there is another way of dealing with something like that. So what is the expected value of x squared? What is the expected value of x squared? Just mathematically. It is the integral or the summation x squared fx of x dx. Can you immediately see that this will be non-negative? Immediately from the integral, right? This is non-negative, this is non-negative. So, and you are making an integral over them, it's non-negative. Okay, so we will create new random variables. Those are x prime is x minus e of x over sigma x. Y prime equals y minus e of y over sigma y. When you look at these two new random variables and think about them, they are just normalized versions of the original random variables. They keep the same amount of randomness, but just with zero mean and unit variance. That's the only thing. It's just normalization of the original random variables. And then we try to get the expectation x prime plus or minus y prime squared. And this thing equals the expectation of big bracket x minus e of x squared over sigma squared plus or minus 2 x minus e of x over sigma x y minus e of y over sigma y plus y minus e of y squared over sigma y squared. And we already know this is greater than or equal to 0. All right, let's look at this. When we enter this expectation sign here, what will this be? Go ahead, be active. When you enter the expectation sign here, and you get ex minus ex over all squared, this is what? All of it is 1, right? But this term alone will end up being the variance, right? Good? The same thing here, this ends up being sigma y squared. When you enter the expectation sign here, what will you get? What's up? Exactly, you will get on all of it sigma xy, right? And thus, this becomes sigma x squared over sigma x squared plus or minus 2 sigma xy over sigma x sigma y plus sigma y squared over sigma y squared greater than or equal to 0. Thus, 1 plus or minus rho xy greater than or equal to 0 minus 1 less than or equal to rho xy less than or equal to 1. All right, let's look a little bit at this proof Sometimes it is quite useful to visualize a proof from the end point, from what you want to reach, because we did not really follow an orthodox way of proving this relation. We just invented two random variables and tried to use the two random variables that we invented. So sometimes it is useful to think about what you want to end up having in order to start a brand new idea for a proof, and this is an example. All right? Good. What is the expected value of a function of two random variables? It's exactly the same thing we did for functions of one random variables, gxy, fxy of x and y, dy, dx, and you sum if discrete. Let's give an example on that, which is example 2. So find the expected value of x squared e to the y for x being a zero mean unit variance Gaussian and y being a uniform in the interval 0 to 3, and they are independent. We just put the relation of this expectation, so the expected value of this function x squared e to the y is the double integral of x squared e to the y f xy of x and y dy dx. All right, fx of x, we already know it, 1 over square root 2 pi e to the minus x squared over 2. X is from minus infinity to infinity. What is fy of y? One over 3 in what range? In this range, right? The given range, 0 less than or equal to y less than or equal to 3. Now, what is fxy of x and y? Multiplication of the two, exactly. Thank you. So fxy of x and y is fx of x times fy of y. And thus the expectation we are seeking becomes, we can simplify the integral immediately from y equals 0 to 3, 1/3 e to the y, integral x minus infinity to infinity, x squared 1 over square root 2 pi e to the minus x squared over 2 dx dy. Again, can someone help me and say, what is this? Exactly, right? The expected value of x squared. Thank you. So this is the expected value of x squared, which is the variance of x plus the expectation overall squared. We know this is 0, we know this is 1, and thus this integral becomes pretty easy, and it ends up being 1/3 e to 3 minus 1. One common thing we observe a lot in these types of integrals, that these integrals are not easy when you have x squared into the exponential of an integral and you don't have something function of x here. So you got to search for tricks. Here the trick was that this is the second moment. This is the expected value of x squared. All right? Any questions? All right, good. Functions of pairs of random variables. We have already discussed a standard way of handling this, which starts from the CDF. the probability of z less than or equal to z, the probability of g, x, and y less than or equal to z, where we are talking about z being a function of x and y. How to handle that? It's a double integral for all the points x, y in this R z, fxy of x and y dx dy. Once again, what you have after the integration sign is always PDF. You integrate PDF. Where will the function of the two random variables show? It will show here. It will only show in the limits of your integral. You will never have your function showing up here. You don't integrate this function, you're calculating some probability. The CDF is a probability, right? So RZ is characterized by G of X and Y. Important special cases that we will prove sum of two random variables. Fz of z equals integration on x fxy of x and z minus x dx. Z equals x plus y. And sum of independent random variables fz of z is integration over x fx of x fy of z minus x dx. What is this thing? Exactly, thank you. So this is the convolution between the two PDFs, fx of x convolved with fy of y. That is something we know from probability courses, that when you have a sum of two independent random variables, the resulting PMF or PDF is the convolution between the two contributing PMFs or PDFs. Why? Let's prove that. First of all, let's recall an important relation. So if we have function h of z that is integral from a of z to b of z, h of x and z dx. What is d h of z by dz? Recall your calculus courses. This is a very important starting point that will help us perform this proof. And it will help that this relation stays in your mind based on well-grounded illustration. What is this?
Inside, and calculate the limits.
What's up?
Inside the integral, I'm using the integral limits.
So you want to take the differentiation inside here?
No, it's the derivative of xz respect to z is inside h, small h, xz.
Yeah, so you want to take the differentiation inside this.
Yeah.
How about these two? Okay, you might not be recalling it now, but how many of you has seen this before? You have seen it before, that's for sure, right? Okay, let's try to think about it fundamentally first. Think about it fundamentally and after we understand what is going on, we will get to the answer. You have an integration between something that is function of the variable you are differentiating on. The two limits are in addition to what is inside. So first of all, before writing anything, how many terms do you expect to have? If you have this, this, and this, how many terms do you expect to have? 3, right? There has to be a term function of the derivative of this, and this, and this. There has to be the case, right? Okay, so first of all, you will have this. Second of all, you will have this. And third of all, you will have the term our friend here referred to, which is the integration from a of z to b of z partial hx of z by partial z dx. All right? This is how you differentiate an integral with varying limits. All right? Okay. Let's try to relate this to the problem we are facing. We want to get fz of z, which is probability that x plus y less than or equal to z, which is probability that y less than or equal to z minus x. All right, let's get this r of z plane and try to perform the integration. What is the area we are integrating here? If this is the line y equals z minus x, is it this area or that area? Right? It is that area, right? The area below the line. So we are integrating for this area. If we pick our infinitesimal stripe to be here, let's try to perform this integral. So fz of z equals double integral. Can someone help me? What is the range of x and what is the range of y? What is the range of x? Thank you. Minus infinity to infinity. This stripe is not really a good stripe. So x is from minus infinity to infinity. How about y? Not x. Yeah, from minus infinity to the line, right? So from minus infinity to z minus x. But we want the PDF fz of z, which is d fz of z by dz. Here comes this important relation that we will use, relation star. So from star, can someone tell me how many of these three terms will end up having here after the equality sign? Some terms will get cancelled. What is the only term that will not get cancelled? Is it 1, 2, or 3? This one, or this one? Who said 1? Yeah, thank you, exactly. That's the only term that will remain. The lower limit of the integral is constant. What is inside the integral is not a function of z. So these two terms will go away and the only term that remains will be this term. So we have integration from x minus infinity to infinity, d by dz, the integration from y equals minus infinity to z minus x. That's the only thing that is function of z, fxy of x and y, dy dx. The differentiation of this is 1, d by dz, this thing is 1. And you make the substitution immediately, so it becomes integration from minus infinity to infinity, fxy of x stays as it is, y becomes the upper limit, z minus x dx. All right? One little thing is remaining. What if they are independent? This is like the easiest step. In that case, what will happen? What will happen to this? Exactly, this becomes a multiplication, and it is fx of x, fy of z minus x dx, and the convolution emerges. All right? Let's do a standard example, but we will do it from the basics and the fundamentals. And then after that, we will try to do it through convolution. But before the example, one quick comment that I always tell you, and you will keep hearing from me as long as I'm giving these lectures, I'm giving courses in general. What is more important than the knowledge is how to get to the knowledge. If you have in your mind that, oh, sum of two random variables, convolution, and then, for example, they are dependent, you get confused. I don't recall whether it was general or only for the independent case. What's more important than the knowledge is how to get to the knowledge. No need to prove this every single time, but if it is in your mind, you know what is going on. You know that, okay, this is the original relation and the convolution emerges because of the independence. All right? Let's do this standard example. So example 3. We have x and we have y, independent uniform, random variables in 0, 1, and you have z equals x plus y, find fz of z. Solution. We will divide our plane of z into 4 regions, but before the 4 regions, before doing anything, just by virtue of looking at this relation, what will be the range of z immediately? Exactly, 0 to 2, right? The minimum value is 0, the maximum value is 2. So you already know that you will get absolutely nothing out of this region, right? For the PDF. So region 1, when you have z less than 0, you immediately know that fz of z is strictly 0. Region 2, 0 less than or equal to z less than or equal to 1. Let's draw this. We have x and we have y and we have this square and we are here. Again, before plotting these lines, the 4 regions will look like this. You will have this region where you are behind the square, where you are above the square, and where you are below its diagonal, but inside, above its diagonal, but inside. Those are the 4 regions, right? Not every problem will need 4 regions, obviously, but in this case, this is correct. So if we take the stripe here, and this is the point z, and this is the line y equals z minus x, we are integrating on x and on y. Can someone tell me the ranges? What is the range of x? We want this triangle. What is the range of x? From 0 to z, thank you. What is the range of y? Thank you, exactly. From 0 to the line. 0 to the line. So from 0 to z minus x. What should we put here? What should we put here? Yes, exactly. So this is fxy of x and y. Fxy of x and y is fx of x, fy of y. Everything is 1s, 1, 1, dy, dx. This ends up being the integral from 0 to z for x, z minus x dx, and it is z squared over 2. The differentiation fz of z is d fz of z by dz, which is z for this region. All right, let's do region 3. Again, for region 3, we are leaving the square, but still we are inside it, so we are here. And this is our stripe. Can someone tell me what this point is? What is this point in terms of x? This is 1, so it has to be something less than 1, right? So what is this point? Exactly, thank you. So this point is z minus 1. So we want to get this integral, so we have fz of z for region 1 less than or equal to z less than or equal to 2 equals. We don't really want this triangle. We actually want this ugly shape. But this ugly shape will require lots of integration tricks and tricks as far as the bounds goes and stuff, so we can do a trick that help us avoid that. What is it? 1 minus another triangle, right? Thank you. So it is 1 minus the double integral on x and y. We know that this is 1. We know that this is 1 dy dx. What is the range of x? Thank you. From z minus 1 to 1. What is the range of y? From the line to 1. From the line to 1. So from z minus x to 1. Right? So this would be 1 minus the integration x equals z minus 1 to 1. 1 minus z plus x dx. That ends up being, for the interest of time, minus 1 plus 2z plus, or minus, for that matter, minus z squared over 2. What is the differentiation of this thing? What is the differentiation of this? Right, 2 minus z, yeah, someone is saying it. 2 minus z, and as far as region 4 goes, z greater than 2, fz of z is 0. So let's draw the final answer, which is something we already know from the beginning. It looks something like this. From 0, 1, and 2. And this value is 1. This is z. This is 2 minus z. Shall we check some PDF properties? Is the area under the curve 1? Right? Half times 2 times 1, right? So the area under the curve is 1, and all the properties are satisfied. The last question in the first lecture that we want to do together is, what if y, the random variable y, is uniform in 0, 2 instead of 0, 1? That is, y looks like this as far as its PDF goes. Before we try to answer this question, this result is already expected via convolution, right? So we did something from the basics that already the convolution is telling us, and we can use the convolution, but fundamentally we managed to just demonstrate it once again, step by step. This time, let's try to do convolution immediately. Can someone immediately tell me the final answer for this? because of the convolution. What will fz of z look like? Go ahead.
It goes from 0 to 3, and first there is a ramp, then a constant time, and
Exactly. Thank you so much. First of all, it goes from 0 to 3. 0, 1, 2, 3. What is the value up here? It is this, right? Last question. Can someone justify intuitively to me this? Why is it constant here? The PDF is constant in that regime. Just intuitively, from the basics of convolution.
Interval is 0 to 1. It's shorter.
Yes, exactly. The interval is shorter. So in an intuitive way, you perform the convolution as follows, right? This is not even intuitive. This is actually even strict. If this is your fx of x, this is your fy of y, y, and x. You flip and move from the left-hand side right, okay? So you have 3 regions. Region number 1, where this one is still emerging inside, right? Region number 3 is when this one is leaving. Both of them will cause ramps because the final answer, the final result will actually depend on z, will depend on the shift. The only region where it will never depend on the shift, it will be between 1 and 2, where this thing is entirely underneath the bigger one. Okay? Any questions?